Good day, everyone. Thanks for joining us. I'm glad that you were able to make it, and I wanted to kick off with a few introductions and housekeeping items. Again, thanks for joining. Today we have a MIPI webinar, a new MIPI RFFE for the emerging 5G era. So today, the presentation is offered by Jim Ross. He's the MIPI RFFE Working Group Chair, Lalan Mishra, MIPI RFFE Vice Chair, and Victor Wilkinson, MIPI RFFE Vice Chair. So just a few things to mention before we get going. All of the telephone lines have been muted upon entry, and the session will be recorded. We'll make that available by the end of the day today on the MIPI website within the Knowledge Library. We'll also make a PDF version of the slides available. So we're looking at a 60-minute session, take about 45 minutes for the presentation itself, and then we will open up for a Q&A session. During the Q&A, there's a few ways that you can raise a question. Primarily recommend that you type your question in either the chat or the Q&A window, or you could raise your hand within the chat and Q&A window if you wanted to verbally ask a question, and at that point I could unmute your line. So without further ado, I'd like to introduce Peter Lefkin, Managing Director of MIPI Alliance, for a brief introduction. Thanks, Peter.
Great, thanks, Dervlan. Thanks to everybody who joined for today's call. There's a lot of interest in MIPI RFFE, and we're pleased to be able to provide you with some additional details with regard to the latest release. I'm going to spend just a couple minutes on about MIPI Alliance for those who may not be fully aware, and then the RFFE leadership team I'll hand it off to them to go through the MIPI RFFE part of it. So let me get on with my part of it so we can free up time for the main portion of the agenda. So MIPI Alliance I'm not going to go through all of MIPI Alliance's history, but we've been around and formed in 2003, and really our reason for being at the time was formed to standardize camera and display interfaces within a mobile device. And you can see that phone. I still see some people carrying those phones today, surprisingly, but that was our real reason for being. And those two specifications in particular, camera and display, and couple that with RFFE as well, are our most widely adopted specifications by far. And that has kind of evolved and built upon over the years as mobile has evolved as well. Looking at the Alliance's member ecosystem, it's an important aspect of MIPI's success. We ended the year last year with over 339 members. We've had year-over-year membership growth globally across 27 countries. And our ecosystem has changed and evolved over time. From MIPI's formation, it was really the application processor developers, the device OEMs, and the semiconductor companies. And as MIPI evolved and MIPI specifications became prevalent and adopted and implemented in mobile, the ecosystem evolved and shifted and included a number of different supporting entities like the software providers, IP and VIP providers, test labs and test equipment companies, as well as auto OEMs and tier one suppliers for automotive, and other consumer electronics companies cutting across many different application areas. And so this has expanded over time. This continues to evolve, and on a weekly and monthly basis, I continue to get surprised by the types of members joining MIPI and interested in MIPI from industries that you wouldn't have expected when MIPI was first formed. We're not going to be able to, obviously, today we're focusing on the left-hand part of the mobile system diagram. We have 48 specifications cutting across and used for many different application areas: automotive, IoT, medical, avionics, wearables, industrial. And one of the fundamental success factors, I think, for MIPI, even from the beginning, was that MIPI specifications were able to be implemented on a royalty-free basis within mobile since our inception. And what we realized over time that for the non-mobile or beyond mobile applications, there was a reasonable non-discriminatory RAND IPR policy that last year, at the beginning of last year, we decided to update and essentially make it royalty-free for all specifications, regardless of where it's implemented. And I think that continues to be one of the success factors and differentiating factors from many different organizations out there, that for MIPI members, you're able to adopt and implement the specifications on a royalty-free basis. With that, I want to turn it over to give a good focus and technical depth to MIPI RFFE. I'd like to congratulate the team and the leadership of RFFE for reaching the v3.0 milestone. And let me hand it off to Jim Ross, who's the RFFE Working Group Chair. Thank you very much, everybody.
Thank you, Peter. Very good introduction. I want to first start off, I recognize a lot of people on the attendees list, people I have seen in the past. There's some new people. I want to start off this presentation with the background on RFFE. RFFE has been around for relatively 12 years now. I think we started in the summer of 2008 as we formed within the MIPI organization. At the time, there was a lot of different fragmentation in the ecosystem of the RF front-end control. We had all kinds of different SPI interfaces being defined to actually control these RF devices. And at the time, a lot of the vendors were making multiple versions of the same exact device just so they could operate in a particular OEM. Since then, that was the main catalyst for RFFE Working Group to form. After they formed, I don't know if it was more of a matter of timing, luck, a good specification, or whatever the reasons were, but when we released our spec in 2010, we essentially became the de facto standard for RFFE control in the mobile handset. And if you look at today, there's relatively, 1.5 billion handsets sold worldwide each year. And if you look at the RF front end, typically in the handset, there's anywhere from 10 to 15 RFFE devices. So you're easily talking north of 10 billion RFFE devices per year just in the mobile handset market. So, RFFE is always trying to keep on top of the new challenges in the mobile handset, but we've also, been very much part of automotive for many years, especially when you're talking about the cell-based emergency communication systems you'll see in automotives. We're also in IoT, anything with a wireless communication, for example, Wi-Fi, definitely the cellular end of things. Anything that has to have wireless communication, transmitting and receiving data, you need to be able to control those devices. Typically, those devices, you have an RFIC master device, but you also have on the slave side, and there's usually multiple of these, you have power amplifiers, you have LNAs, you have switches, you have antenna tuners, there's all kinds of, you have couplers, you have all kinds of different RFFE components that need to be controlled. So I'm going to jump to the next slide. So just a brief history of the evolution of RFFE. Like I was stated earlier, 2010 was our first version. Essentially, it was the first release. It ran at 26 megahertz. And the reason I highlighted triggers is because many of the main additions in V 3.0 are trigger-based. And before I have Vic and Lalonde get into the major trigger features that we're adding in 3.0, I kind of want to build a story why triggers are so important in RFFE and also why 5G is driving the need for the expansion of these trigger features. So, like I was stating, in 2010 was the first version. We shortly thereafter released a 1.1. There wasn't really any major functional additions. It was just cleaning up the spec and a few minor enhancements. In 2014 was our next major release, and what we did there was we doubled the bus speed from 26 to 52. We added multi-master support, and we added a feature called synchronous read. Shortly after, relatively 4 years, 3.5, we created 2.1. There was a lot of new content on that one too. We had the masked write, the master context transfer. We added extended triggers, and the triggers, like I said, are going to be the major focus of this presentation. And shortly after that, in 2020, we just released 3.0, and that is all trigger-based. And as you can see, by this timeline, in the last few years, RFFE has been extremely busy, and that is mainly due to the needs we've discovered through, the evolving 3GPP standard and 5G. So just to explain a little bit why 3.0 is driven by 5G. If you look at 5G, you definitely have the extreme high data rates, but you also have the ultra low latency requirements because of mission critical control. And just the sheer number of devices that you have to control out there that are on the network, it just expands not only the number of devices you need in the RF front end to be able to handle all this traffic and lower latency, but it also drives the control of those devices, and that's what RFFE does. The graphics on the right essentially show that the increase of the subcarrier spacing, and with that increase, you have a shorter time slots that you can configure your RF front end for that wireless communication. And so with the higher order MIMOs, it definitely creates a lot of new challenges with RFFE, and the timing budget is very much shortened as far as being able to align everything to time precise configurations. And that is why triggers are so very important. So if I jump to the next slide. So one of the main things people noticed in 5G is just the pure data throughput and the data rates required. This is a lot of times due just to the video portion of a phone, both upload and download, the high quality to receive and send all that information. I mean, to physically see it, you have to have a very good display, but to be able to wirelessly send that information to the handsets, you have to have RF devices that are able to handle those peak data rates. And you also need to be able to be very precise in that configuration. And when Vic gets into the time trigger portion, he will explain further on the 20x timing precision improvement that we actually see with some of the new features added in 3.0. So just to expand a little bit on why timing precision is so important. So essentially, like I was stating earlier, on an RF front-end subsystem, you have your master devices, but then you have all kinds of different slave devices. You have LNAs, you have PAs, you have antenna tuners, antenna controllers, couplers, and many times you have multiples of those because you have to control the different bands. You have low band, high band, mid band. There's a magnitude of different devices out there on the RF front end. And essentially you're trying to synchronize all that control over one bus. So if I had it noted earlier, RFFE is a multi-point bus. So many times you'll have one master or multiple masters controlling that bus, but you'll have up to 15 different slaves that are actually all in sync with each other with their switching configuration, and that's where RFFE comes in. In addition to the timer precision, the new 5G requirements also requires us to add additional triggers. We have the narrowing timing budget with the slot times decreased and subcarrier spacing increasing. So the solution targeted for that was the time triggers. And you also have the mapping of the triggers, and that portion Lalon will get into. But we also added the new feature, Mappable triggers. So just to give a little background on the evolution of triggering in RFFE, with the release 1.0, we defined 3 different triggers in the RFFE spec. At the time, people thought, that's probably overkill. We only need 1 trigger, but the working group was trying to be proactive, so we defined 3 different triggers. And essentially, what that allows us to do in a configuration environment is you have these different controls in a particular device and or shared in multiple devices on that bus. And there's precise times you want those controls to be in sync with either within that device or within the devices on the bus. And that is done with the triggering mechanisms within our RFFE. And to do that, you can do commands that are particular to one device, or you can also do group commands that target multiple devices on that particular bus. So just a little better illustration of that fact is typically you will preload registers, which we call shadow registers, before an action actually has to take place. And the timeline on the bottom of this graphic shows you loading the different registers, A through F. But at a specific, very specific time, you want those triggers to take effect. Those functions, those controls to take effect on those RF front-end devices. and that's where triggering comes in. And for example, trigger 0 could be multiple registers in one device, or it could span multiple devices. Likewise with trigger 1 and 2. One thing that we did in the original spec was when we defined the triggers function, we included it in one reserved register. And that actually made our life somewhat difficult because in that one register, it's an 8-bit register. We not only had the trigger firing mechanism, we had the mask bits, we had the RFFE low power mode, and we had the software reset bit all in that one register. So whenever that register was written, there was a lot of different things in play there, and some of those bits were actually you could only update them via the USID, and some you could update via the group slave ID and the USID. For example, the mask bits are only updatable with the USID. So for many years, I think if I look back at the timeline, we released 1.0. 3 triggers was more than enough. We really, a lot of people use 3 triggers, but there was a time early on that people would actually OR all 3 triggers together because we never thought we needed more than 3 triggers. But with MIMO configurations and really with the LNA positioning in the RF front end, it really drew the need for more triggers. The LNAs were essentially pulled out of the RFIC masters into the closer to the filters and switches for lower noise figure, and with that you had a lot more control you had to do over the RFFE bus, and that really drove the need for 2.1 and additional triggers. Shortly after that, with the emergence of 5G, we knew that, these extra triggers, just those alone are not enough to meet the needs. We really need tighter timing precision, and we need to be able to reconfigure those triggers. So within 2 years from 2.1, we developed 3.0, and those are really the main functions that we're going to be describing today. That's the time triggers and mappable triggers, but those were some big enhancements for the triggering of RFFE. And this graphics essentially just breaks down, what the new additions were going into, the different versions. RFFE 1.0 had the 3 triggers. Then we added an additional 8 in 2.1, and 3.0 we added yet an additional block of triggers. But the main thing is we added time triggers and mappable triggers. So at this point, I'm going to hand Vic the controls, and he can dive into some of the more top-level details of the time triggers.
Thank you, Jim, and welcome everybody. Thank you for joining us today. My name is Vic Wilkerson, and I'm Vice Chair of the RFFE Working Group, and I'm going to present some of the details of the time triggers feature that was added in RFFE 3.0. So in this graphic here, what we're trying to show, and the example uses extended trigger 3 and 4, but before time triggers, you can see in the top graphic that if you weren't firing two triggers simultaneously, then the closest that they could be spaced in time was the length of the command sequence necessary. That being for the standard triggers, one can use the register write command sequence in RFFE. For the extended triggers, since they're located much higher up in memory, those have to be with the extended write command sequence, and one can do that with just a one data byte, but still that's the minimum amount of time. So as you can see in use case 2 in the bottom, if you try to pull those trigger actuations, or we often refer to them as firing, closer together than the length of the appropriate command sequence that as a minimum must be used, then you fail. And that's what's indicated by the fact that the trigger is being blocked. And you can see that's because the second command sequence would need to begin before the first one has expired. So the spacing for the standard triggers translates to, at 52 megahertz, translates to about half a microsecond, is the closest that delta T can be. And for extended triggers, it's actually about 0.65 microseconds. So sometimes this caused difficulty in applications, and so time triggers was developed to overcome this on the same RFFE bus, that is. So as you can see in this example, again, it's just by example, it's extended 3 and 4 again, but in this case, with the time trigger feature, the two triggers can be fired as closely spaced in time as, of course, still simultaneously, but assuming that simultaneous triggering is not desired, they can be spaced apart in time by 1 S clock cycle. So this greatly improves the situation, as compared to what's available with the standard trigger firing mechanism. So if we move and get a little bit more into some detail as to how this works, let's say that you want the spacing of a set of triggers to be as shown in the right-hand side here, T1, T2, T3. And then you can, ahead of time, set up the loading of the shadow registers as Jim was talking about. And in that case, they're color-coded and just A, B, and C corresponding to triggers 1, 2, and 3. So the scheduler needs to, in the master device, needs to compute ahead of time exactly what those times need to be, and then simply, as was shown in the previous slide, the way that these time triggers work is that there's actually a countdown timer that's associated with each distinct trigger. And so once these desired times are computed, and based on the number of clock cycles, up to 512 out in time, is when this needs to happen, then the master from that point simply keeps the S clock running, and once each of these triggers reaches their countdown, as you can see, then the triggers are fired without having to issue an RFFE command sequence. So this can be very powerful feature, we think, and help solve the issues that we're seeing, in prior versions of RFFE. So the cost in a slave, this is then the slave side. As you can see, then each of the extended triggers, because again, the extended triggers must be used for time triggers. So this is the block A set, which is from triggers 3 to 10, and in this case, it's showing up to 8 counters could be inserted into a device, and then by whatever means, once not only the UDR is loaded into the shadow register, but the time trigger counter is loaded. If it's loaded with some value other than 0, then on every clock edge of S clock, the counter will count down. And so the cost for this, though, is that for each distinct time trigger action that's desired in the end device, there must exist one of these counters. Now, judicious use of those, if one takes a look at all their needed scenarios, would be to assign to a given trigger multiple options or multiple uses, and this can help cut down on the number of counters. But obviously, the number of counters that's needed is going to be somewhat constrained by the fact that you've got to sort of worst case things, right? So with that, it's important to, I might add, these counters are actually 9-bit counters. I didn't actually get into the details, but with it being a 9-bit counter, the upper 8 bits are loadable, and then whenever the counter is loaded, the LSBs always reset, or yes. So that is in essence how time triggers are defined and set up by a user to operate. And one thing to add to that is that I was mentioning, the fact that one needs a counter for each one of these triggers, and that's true. Although, as will be shown by Lon in a moment, it's important to note that time triggers and mappable triggers can actually coexist and can actually work in concert with one another. So with that, I will turn it over to Lon and let him speak to the mappable triggers. Let me flip that first slide for you, Lon. And one more thing I'll say is more cowbell.
Thank you, Vic. So let's go to the next page. Okay, before I jump into the details, very quick recap. You heard from Jim that RFFE 2.0 had only 3 triggers, Then on 2.1, we added 8 more. We call them extended trigger. And with now the newly released 3.0, we have added 7 more. That brings the total number of triggers to 18. And out of these 18, 15 are of extended trigger type. And over these 15 triggers that we have 2 properties or functions that are applicable. One is called the time trigger, which we just described. What I'm going to describe next is the mappable trigger, which is again a characteristics which is applicable to these 15 triggers, if you will. So what do we really mean by mappable trigger? The concept is rather very simple. And I have this simple diagram to illustrate this for you. Unfortunately, you can't see the movement of my cursor, but please follow my words as I try to describe them. So on the left-hand side picture, you will see that what we have described here is what you would call as the hardening of trigger association. What it means is that at the design time of the device itself, the designer has associated a particular trigger with a particular trigger element. In this simple example, we have taken the case of ELNA, where the trigger bit, which is related to the D0 bit of the trigger activation mask register and trigger register, is mapped to this particular element. What does that mean? It means that for the remainder of the system's operation or the life of that product, the ELNA element in this example is always going to remain locked to that particular trigger. You do not have the flexibility to change it. Now, this situation brings several challenges for the system designer. One is that you have the trigger which is permanently mapped, the trigger number permanently mapped, you cannot change it. And also, if you are designing a very complex system, you have to, you really can't encompass all possible use cases and be able to think that what trigger number should be associated with a particular element. In simple words, it brings more and more complexity, primarily as we are now venturing into the 5G space, where the front end is getting even more complex. The dynamic trigger association mapping has to change because of various requirements, but you're locked because of this hardening. And that was the fundamental requirement why we were forced to think to bring additional functionality into RFFE 3.0 trigger functionalities, and that's where mappable trigger came. Now, as the name suggests, the mappable trigger is basically you should be able to move the mapping of the trigger for a particular trigger element to any trigger that you are required to. So you're not tied down to a particular trigger number for a trigger element, but you can assign a particular trigger as you wish or as your system requirements requires you to do. So let's see, for the same example that we saw on the previous page, we are extending here. What we have here, I have shown 3 different configurations just to illustrate the idea. So on the configuration 1, you will see that the same trigger element was mapped to D0 bit of the trigger registers. In the second configuration, you see that we have arbitrarily moved it to the mapping of D2 bit. And on the last one, configuration 3, you see it mapped to D5. So based on what mapping you require, you can dynamically make these changes and make your system meet the requirement that you have in hand. But one thing worth noticing here is that with every trigger, of course, there is the shadow register and the actual control register element within the trigger element. That mapping is not changed with mappable trigger. So that mapping remains absolutely the same that you had. Only thing which is changing is the mapping of the trigger itself, which is going to cause the data flow between the shadow register and the actual trigger element. Going further, so now the question is that how do we tie all these things together? So we have the trigger, time trigger, we have the mappable trigger, and that is what we have tried to show here in this particular case. So because of these additional triggers that we have, not counting the PM tricks, we have the block of 8 triggers and another block of 7 triggers. All these are extended triggers, as I said in the beginning. And these are what we have classified. If you use all 15 of them together, let's say we call them block AV. And as you can see here, these the trigger mask and the trigger register is how they are configured, or how the bits or the grouping is done is what is illustrated here. So essentially what happens is that as you are configuring a particular trigger, you basically need a mux to map the trigger as you wish. And because there are 15 of them, 4-bit is sufficient to map them to any particular trigger element as you wish or as your system requires. So going further, here you will see that we have shown the block A configuration, just for clarity. So again, the top two registers here in yellow color is the trigger mask and trigger register. Now we are bringing this counter. What does it mean? It means that the counter registers are basically associated with the time trigger element, which Vic was describing a few minutes back. So if you don't want to fire a trigger by sending a traditional mechanism of sending a datagram, you have these counters preloaded, and you make these counters operate over the S clock. It is important to note that the slaves do not require a local oscillator for that purpose. The counters get their clock from the S clock of the RFFE bus itself. So either you can trigger a trigger by a datagram, that is a conventional method, or you can trigger them by these counters as per the mechanism of time trigger. The mapping is all that is the part of this mappable trigger. And like I said, because there are 15 of them, we need 4 bits to map these muxes to map the trigger to a particular trigger element. So if you see the trigger register utilization at a very, very high level, then this is what it currently looks like. All the trigger activation mask register and trigger register themselves, also as well as the counter, where the count value that you supply in the datagram, which is an 8-bit value for different counters, they all are mapped into the RFFE reserved register space. So you don't have to worry, it's part of the standard. Everyone will follow the same map. Now, as far as the shadow register goes, shadow registers and also the mtrig mapping register, there you have the flexibility to put them anywhere that you want to inside the UDR or the user-defined space. So this is not per the MIPI specification. It is within your flexibility, within your system requirement where you want to keep them. And then the very end of the register map is again a register reserved space as defined by MIPI RFFE spec. So to sum it up, I would say that RFFE 3.0 brings 15 additional, total 15 extended triggers. And all of these 15 triggers can have the property or the feature of time trigger and map trigger. Now, the key question would be that do we require to have the map trigger and time trigger enabled for all of these 15 triggers? Not at all. It all depends on your system requirements, so please read the spec, and there is very thorough guideline given there, how you have to group them and how you have to use them. But the implementation will actually depend on what your system requires and how you want to design your device. So I would stop at this point of time and pass it back to Dervila. And actually here is the MIPI RFFE next step. And Jim, would you like to talk through about it?
Yes. Did you pass the slides over?
Yes. Should have it.
Okay. Thanks, Vic and Lalonde, for the explanation of the 2 new trigger features in RFFE. And before we get to the Q&A, I just want to remind everybody that 3.0 was adopted the end part of April, so it should be up there, should be available for review for the adopters and contributors. The working group is also completing work on 2 supporting documents. That is the application note and the FAQ. We're getting very close to wrapping those up. Hope to have those done either by later this month or early next month. And as noted earlier, RFFE is always an evolving ecosystem, and especially with 5G. So, we are definitely moving forward for our next version. And, we are just starting to look at different proposals, thinking about, what we have to do to meet the 5G capabilities. And we're also looking at the challenges of millimeter wave, which is new radio 2. So we're definitely looking for ideas from working group members, especially from the system side of the industry and the master side. Historically, they have really driven the needs in RFFE, so we definitely encourage people to get involved. So at this point, if you guys want to learn more, and if you're not a contributing member, you can definitely go to MIPI.org and find out more information about MIPI. And for contributing members, all the RFFE information, all the documents, all the proposals, presentations, and so forth are available. At this point, we can go ahead and open up the floor for questions.
Thanks, gentlemen. Appreciate it. So yes, encourage questions to come in the chat window or in the Q&A window. And I do see a question here. With all these versions of RFFE, can a V.1 device work on the same bus as a V3.0 device?
Okay, Derval, I can take that one. So essentially, RFFE is really stressed on backwards compatibility. So as you look at all the features from the evolution of RFFE, most of those are optional features. So they're essentially add-ons to address new challenges in the RF space. For example, the mappable triggers and time triggers are optional features. So theoretically, if you have a 1.0 device, a slave device, it could potentially operate on the same bus as a 3.0 device, assuming that the bus speed is at 26 megahertz. Another example would be if you have a 3.0 device that supports time triggers and mappable triggers, but you want to be able to use that device in a 2.1 system, you can definitely use that device in 2.1 system, but you would not be able to activate those certain optional new features. So RFFE is definitely always stressed backwards compatibility because there's just, like I said earlier, just, tons and tons of devices out there. And I know 5 versions might be a lot to some people and might not be a lot to some people, but over 10 years, as you go from version to version, some systems are very simple, some are very complicated, and being able to mix and match different versions of the spec on the same bus with, of course, some limitations, RFFE gives you that ability. Okay, next question.
Thanks, Jim. Next question. Can you explain why timed triggers can actually reduce the number of RFFE buses needed in an RFFE front end?
If you don't mind, Vic, can you take that question since you're that expert?
Sure. No, that's a very good question, actually. Let me preface my answer by saying first that there could be lots of reasons why somebody would need multiple RFFE buses. could depend on system architecture, could depend on a number of other factors. But one potential reason that people might do that, if people remember the first slide that I showed, where you could see that there was a limitation on the spacing between between triggers because of the length of RFFE command sequences. One way around that in the past would be to put two different devices on separate buses, and then one can arrange for the command sequence on one to be aligned appropriately so that you could get that spacing. But you can imagine that if you had to do that just for, in the absence of time triggers, and that was the only reason, it could add up on the number of buses that are needed. So time triggers potentially can help people reduce the number of RFFE buses that have to be deployed in the system.
Thanks, Vic. Okay, let me just check and see if another question has come in here. Yes. Can you explain why timed triggers can actually reduce the number of RFFE buses needed in an RFFE front end?
I think that's the one we just had, Dervla.
That's right. You're right about that. Apologies. Can you describe how mappable triggers can be used to recognize the LNA path in RF subsystem?
Can you address that, Lalan?
Yes, sure, Jim. So actually, as you saw in the very introductory part of the slide deck, the 5G RF front end is complex in the sense that it is going to use various RF bands. And as you are, making dynamic configuration, again, based on how your system is performing, for example, you might be using one MIMO configuration and then changing to another MIMO configuration, or instantiating different RF bands at the same time. One could be working on the traditional cellular band, other could be working on the newer millimeter wave or sub-6 G band, or as we are adding further bands in the higher frequency range. So all these things combined together could be introducing sufficient level of system level complexity where you have to change the configuration of the front end dynamically. What do I mean by that is that you may have to change the configuration of the switches, how the RF signal paths are changed, how a particular ELNA or PA groups with another set of antenna, etc. Whatever the case might be, because of this dynamic nature, you may have to change the configuration. And that is where you will be required to change the mapping of the trigger to meet all these restricted control timing budget that you have for 5G. And that is precisely where the role of mappable trigger kicks in. So you will be remapping them based on your newly configured front-end configuration that you have, again, based on your requirement. And then you will be, again, triggering them based on the time trigger to meet the best timing budget that you have. Most likely, the traditional approach of datagram-based triggering may not work. If it works, great. If it doesn't work, of course, time trigger is there that we have added in 3.0. Hope that explains. Thank you.
Thanks, Lalan. I do have another question here. Are there proposals for mmWave that MIPI is considering? What kind of challenges are RFFE 3.0 facing towards mmWave usage?
So I can take a stab at that one. So as a working group, we have definitely been looking at different architectures for millimeter wave for the RF front end. And this is something, I guess, has really been a challenge because we really need systems and master companies to bring forward proposals. we are definitely looking at it. There has been some work done in the RFFE working group, to open up the call for proposals, and we've had some discussions, but we definitely don't have an agreed path forward on exactly what we're going to do there. But we are definitely looking for people to get involved and bring ideas to the table. I don't know if anybody else wants to add to that.
Well, I was just going to say, Jim, and certainly what you say is correct. One of the concerns that the RFFE working group has is that just the sheer amount of data that's going to be necessary could be very challenging for the limitations of the RFFE interface itself. In fact, it may be such that it requires a much higher speed interface style, and that would bring with it some challenges in terms of being point to multi-point. There was some work and has been some work that's been done in that area, but as Jim alluded to, we're still looking to try to iron out some of the details that we really need to in order to be able to embark on a full interface specification definition.
Yeah, that was good input, Vic. I mean, one of the biggest challenges we have in looking at those higher speed interfaces, most of them are, like Vic said, point to point, and there are a lot more pins on a package, and a lot of companies struggle with that. So we are definitely looking at ideas, but we're definitely not there for a solution yet.
Thanks. I don't see any other questions. I would ask, we have a couple of minutes left. If there are any, please go ahead and raise your hand or type them in the chat or Q&A window. I do see something in the chat right now saying this might not be appropriate question for the area of RFFE interface. Although, is there any new specification or feature being considered with regards to a low power consumption?
So as far as low power in RFFE, RFFE really strives to be low power, and as Lalonde alluded to earlier, usually there's not even a clock source on the slave devices. There's not a local oscillator. All the clocking is done over the RFFE bus itself, and it's not a continuous clock. So, and a lot of the technologies within the slaves are actually some pretty old technologies which offer very low leakage, but definitely RFFE in a mobile handset power is extreme concern, and that has been the concern from day one, and that's why a lot of things have been defined the way they have in the spec.
Thanks, Jim. I don't see any more questions in the chat or Q&A, so I would say at this point maybe that's a good time for us to close, and appreciate everyone's time today, and thanks to our presenters and Peter. So if there's no other questions, then I would bid you all a good day ahead, and thanks again for joining us.
Thank you.
Thanks, everyone.
Thank you, everybody.
Thank you.
Thanks, everyone.